Hello, thank you for joining the talk. I'm Govindu Saikesava. I'll be presenting on the topic MCS selection for multi-connectivity and eMBB-URLLC coexistence in time-varying frequency selective fading channels. This is a joint work with my research advisor Nilesh P. Mehta, and we are at Indian Institute of Science, Bangalore. So this is the outline of my talk. First, I'll introduce URLLC and multi-connectivity. Then we'll see the URLLC-MBB coexistence scenario. Then I'll present the system model and the optimization problem, followed by numerical results and conclusions. So first, before introducing URLLC, we see what are the use cases of 5G, and URLLC is one of that. So 5G has broadly 3 use cases. First one is enhanced mobile broadband, abbreviated as eMBB. It is expected to cater applications which require high-speed data rates in the order of Gbps, like augmented reality, virtual reality. The second one is massive machine type communications, abbreviated as MMTC. In MMTC, as the name suggests, large number of devices are connected, and it is expected to deliver applications like smart grid, traffic management. The third one, which is ultra reliable low latency communications, it is expected to deliver services applications like factory automation, telesurgery, automated traffic. Now, among these 3 use cases, URLLC is critical. We see now why it is critical. So first thing, URLLC has challenging requirement like reliability greater than 99.999% and a latency of 1 millisecond. For example, consider an application like telesurgery. The doctor is present at a remote location far from the patient, and he sends instructions which is received by a robot which is conducting the surgery. Now we can see that these messages should be transmitted with very, very high reliability. And to meet those challenging requirements, we need novel techniques. First one is multi-connectivity for high reliability, and for low latency, the URLLC data is immediately transmitted on mini-slot level. Now we'll see about multi-connectivity. So in multi-connectivity, multiple base stations transmit the same data. They transmit on the same time and frequency resources, and they employ maximal ratio transmission. In maximal ratio transmission, the signal from a base station is multiplied by a weight which is proportional to the wireless channel gain. Here H1, H2, and H3 represent the wireless channel gains between the base station 1, 2, 3, and the user respectively. The SNRs add up in this kind of transmission. Now, the base stations require channel state information from the user to determine the MCS modulation and coding scheme and the weights, because we saw the weights are proportional to the wireless channel gain. Therefore, the base station requires the channel state information from the user. Now we'll see the URLLC-MBB coexistence scenario. So first thing, static reservation of resources for URLLC leads to wastage. Because the URLLC data is sporadic, we don't know when it arrives, so we cannot reserve the resources for URLLC in static. And also, whenever the URLLC data arrives, it cannot wait till the end of slot. So what happens was, when the URLLC data arrives, it punctures the eMBB data, which is ongoing. We can see here the frequency time grid. The MBB users are allocated some part of frequency, and they are transmitted on a slot level. And we can see the URLLC is getting transmitted on a mini slot level, and it is puncturing the resources which have been already allocated to the eMBB users. This causes the block error rate of the eMBB to increase. So this is the background for the talk. So before going into the system model and results, I will present the contributions. So when feedback delays are negligible, we propose a low complexity algorithm called MCMSA to select the subset of base stations and their MCS. We derive an expression for achievability, which is the probability that at least one subset of base stations and MCS can meet the URLLC error target. We derive the expression in a frequency selective feeding channel. And lastly, when feedback delays are not negligible, we propose a novel stochastic reliability constraint for the URLLC. So these are our contributions. We'll see the system model. So here, system model, base station set B and subset of base stations yes serve the URLLC user. For example, here 1, 2, 3, 4, all the 4 base stations they form the set B, and base stations 1, 2, and 3 are serving the URLLC user, so it forms the set S. We have a controller. It is connected to all the base stations, and it determines the subset S and the MCS for the URLLC user. The MBB users are connected to one base stations, only one base station. You can see here the channel is frequency selective. That means the SNR varies across subbands. Now we'll see why this frequency selective nature of the channel is challenging, and we also see a method to overcome that challenge. So as we know, SNR varies across subband, but the 3GPP requirement says same MCS needs to be used on all the subbands. This is because in order to limit the downlink control channel overhead. So we are given a vector of SNRs now. So what exponential effective SNR mapping does is it converts into a scalar value called effective SNR. It is given by this formula, beta m into logarithm 1 by n summation 1 to n exponential of minus gamma I by beta m, where gamma I is the SNR of the ith subband and beta m is an MCS specific constant. We can see ESM is converting a vector of SNRs. We can see different subbands of different SNRs. It's converting into a scalar value. Now, how to interpret this effective SNR? It can be interpreted as follows. It can be seen as an equivalent SNR in a frequency flat AWGN channel that results in the same BLER as in frequency selective channel. So we've overcome the problem of vector of SNRs and we convert it into a scalar value. Now, once we know the scalar value, how to compute the BLER value? BLER, not value. So to compute the BLER, we use truncated exponential function of SNR. It is given by this formula. BLER of MCSM is Cm into exponential of minus dm into zeta m. Zeta m is the effective SNR. And Cm and dm are the MCS dependent constants. So we have converted the vector of SNRs into a single SNR and we saw how to compute the BLER. Now we'll see the optimization problem. So the goal of the URLLC-MBB coexistence optimization problem is to select the subset of cooperating base stations and MCS that minimizes the eMBB throughput loss while satisfying the URLLC constraints. The objective function is stated like this. Lm is the throughput loss at a base station when m is the MCS of the URLLC user. Since the URLLC data is getting transmitted from subset of base stations, yes, it is multiplied by the cardinality of the set. Now the constraint is interpreted like this. The block error rate of the MCSM at the effective SNR is less than or equal to final error target. We have seen the formula to compute this block error rate. Now we'll see whether any feasible solution exists for this optimization problem and what is the probability of having a feasible solution. We call it achievability. It can be expressed in terms of regularized incomplete beta function. It is given by this formula. Here the C1, D1, beta 1, they're constants specific to the lowest MCS. The beta parameters A and B are given by this formula. Here the GJ and SJ, they're functions of transmit power, noise power, and path loss. Once you know the transmit power, noise power, and path loss, we can compute the GJ and SJ. And N is the number of subbands. Now we plot this achievability as a function of URLLC error target. We'll see how it behaves with the error target. To plot that, we average over different locations. Here is the grid that we used for simulation. The base stations are located at the edges of the grid. The 4 base stations, it's a 300 cross 300 grid. The URLLC locations are given by the red marks. We can see as the error target gets reduced or becomes lower, the achievability is also lower. This is because for lower error targets, the SNR required to meet those error target is higher. So as the error target decreases, the SNR required to meet this error target increases. Therefore, that lowers the achievability. So we plotted for 2 different transmit powers. We plotted both analysis and simulation. So now we have seen this achievability. Now we'll go to the throughput loss part. So the eMBB throughput loss for different MCSs, QPSK 16, QAM 16, QAM are the modulation schemes, and here are the code rates. This is the throughput if you do not puncture in kbps, and this is throughput loss. This is per PRB. We can see as the MCS increases, the throughput loss increases. This is because the higher MCS are more prone to the puncturing. Therefore, higher the rate of MCS and higher the throughput loss. So now we benchmark our algorithm MCMSA. To compare it, we compare it with the conventional. Our algorithm MCMSA jointly optimizes the cooperating base stations and their MCS. The second one, conventional, in it all the base stations transmit without any optimization. We plot it as a function of error target for 2 transmit powers. We can see the MCMSA reduces throughput loss for both the transmit powers. We can see at higher transmit power, it reduces significantly because it uses this higher transmit power, that means the good SNR by SNR. It also, the MCMSA requires fewer computations than brute force search, which requires 2 power number of base stations into number of MCSs. Therefore, the MCMSA reduces the eMBB throughput loss significantly. So this is the first part of the talk. Now we go to the second part, which deals with the time varying channels. So we'll see what is the problem there. So here, the channel state information report comes at time t, whereas the packet transmission occurs at time t plus tau. The channel state information becomes partially outdated by the time of transmission. The instantaneous BLER requirement cannot be met. This is because the controller does not know the instantaneous SNRs from the base stations to the user. It affects the selection of cooperating base stations and MCS and MRT weights because all of these are dependent on the channel state information. If it becomes outdated, it affects the selection of these things. So for this scenario, we propose a new constraint to select the MCS at the time of transmission. It is given by this expression, probability such that the block error rate of the MCSM at the time of transmission is less than or equal to epsilon naught, given the channel state information at time t. This probability should be greater than a value 1 minus delta. It's a threshold 1 minus delta. Smaller the value of delta, tighter is the constraint, and the delta depends upon the use case. So we have seen the constraint. Now we'll see an expression to calculate this probability, conditional probability. The conditional probability, it also can be expressed in terms of regularized incomplete beta function. It's given by this expression. The parameters Cm, Dm, and beta m are MCS dependent constants. And the beta parameters Am prime and Bm prime, they're computed using conditional statistics of the SNR. Now we'll see the effect of this approach. So we use the criteria of probability of meeting the URLLC error target. We compare 2 schemes, ignoring feedback delays. The other one is our proposed approach. We use heat map to represent the probability of meeting the URLLC error target. So the heat map is seen like this. There are 4 base stations. It's a 300 cross 300 grid. We can see the X meters, the distance. The base stations are located at the edges of the grid. The color map here, the color scale represents the probability from yellow to blue. Now we can see as the user moves towards the center of the grid, the probability decreases. This is because at the center of the grid, the choice of MCS is sensitive to multipath fading. Whereas at the base near the edges of the base stations, the user is very close to the base station. As a result, the choice of MCS is not that much sensitive to multipath fading compared to the center of the grid. Therefore, the probability reduces to almost 65% near the center of the grid. We can see the proposed approach markedly increases the probability. We can see even though at the center of the grid it is 93% because we're choosing MCS like that. And throughout the grid, it is much more than the scheme which ignores feedback delays. Now we see the throughput loss as a function of the delay. So throughput loss as a function of FT into tau. It's called normalized feedback delay. FT is the Doppler spread. We can see as FT into tau increases, the throughput loss increases. We plotted it for 2 error targets. This is because as FT into tau increases, the CSI becomes more outdated. Therefore, to compensate that, lower rate MCS is selected for the URLLC user. So to conclude the talk, we address selection of cooperating base stations and rate adaptation for URLLC in multi-connectivity. We derived an expression for achievability in a frequency selective fading channel. We proposed a low complexity algorithm MCMSA that selects the subset of base stations and their MCS. It minimizes the eMBB throughput loss. And we proposed a novel stochastic reliability constraint for the URLLC. So thank you.